Okay, well, thank you so much for volunteering also to present in this last workshop day. So yeah, we've also been very excited to finally hear a little bit on what you're actually working on at the moment. And so it's a little bit more advanced, I guess, because you need a particular microscope to get the kind of data that you analyze with your plugin. But then it's really powerful to have those options. So I'm very curious to hear from you. And yeah, so again, please just briefly introduce yourself, and otherwise, let's start to hear from you.
Okay, perfect. Thank you very much for having me today. Thank you very much for allowing me to be part of this nice event. Especially thanks to Rocco. Besides the really nice presentation, you know, this plugin that he created is amazing. There is a lot of things that you can explode over there. So let me start sharing my screen so we can start. So my presentation.
Yeah, it's good that you show this. So both the Napari Zelda and the Napari Superres plugin now have a section also on the GitHub repository on the Jupyter book of this workshop. So you can even more easily directly access the information there.
Correct. I will point a lot towards that. So here's my presentation. Can you see my screen and my presentation now?
Yes, excellent. Thank you.
Okay, perfect. So my name is Julián Mejía. I'm a postdoc at the National Laboratory of Advanced Microscopy at the Institute of Biotechnology in UNAM in Mexico. We are only 1 hour and 30 minutes away from Mexico City. So I'm really happy to be with you today. Good morning, Latin America. Good evening, Europe. Today I will talk about this plugin for Superresolution, which is based in fluorescence fluctuation microscopy. And you were right, Tobias. Probably you will need specialized microscopes to get the image to process with this plugin, or not. That is part of the thing that I might trigger today, the curiosity. So this is my email. Please feel free to take note of it and send me any question or further support that you will need with it. Okay. So let me start with the story. The plugin started as a hackathon because these two guys, what do I do with it? Okay. Adan is our PI and in a group, and Slay was developing this theory, which is called MESR, as part of his PhD. And after this, they decided to join to a hackathon organized by the Chance Zuckerberg Initiative. And that is how they met together with Raul Rocco. And they created the first version of this plugin, which was done in one night, which is impressive, I would say. This plugin is really nice. So let me start showing you what we have to cover today. So for that, I will refer you to the page or webinar. In here you have the schedule, but then in the day 3, you can go to the Napari Zelda that Rocco just presented, or you can go to the Superres, Napari Superres. In here you have plenty of information. For instance, you have the reference that I will mention right now, and the papers that establish the techniques that we are about to explore. You have also the instructions to install Napari. I know that this is a hybrid session, so there is people that are really expert on how to install Napari and how to handle and probably using the YAML file, and there is people that is not. So please feel free to refer yourself to this webpage and try to follow the instructions. They are quite straightforward. There are two things that I want to highlight. You have this user guide in here. It's quite detailed. You have plenty of information. Actually, we set up more than 50 pages. And I think that, or hopefully, more of the question that you might have about the plugin, you might be solved in here. Another thing that I want to call your attention for those that already attended the event, you have a YAML file here. This YAML file contains all the requirements to do a successful installation to use the plugin. There is one thing that is interesting to me when I started working with Napari. I'm using Windows 11. Windows 11 has a little issue with Qt. For some reason, scramble it a little bit. It's not an Napari issue. It is a way that Windows handles Qt. So an easy way to detect that something is wrong with your computer, especially if you're using Windows 11, is when you open Napari. The font is quite big. It's way bigger than, for instance, the font that you have in your taskbar. So if you have that issue, please just set the environment variable as Qt auto screen scale factor equal to 0. That will fix it and that will do the trick. Other than that, then you are ready to use Napari. And this is a fresh new installation of Napari. I will show you how to install the plugin graphically. Rock and I, we have done plenty of work of that, so we try to make your life easier so you don't have to struggle with commands and that much with environments. So let's start installing our plugin. Let's go to plugins, install plugins. And then you look for Napari Superres. And you see it's the only one that appears. You just click install, and you can see the status. You have it here, all the login details. Now it's already installed, and we have to refresh the Napari viewer so it can load properly. Let me do that. And now that it's refreshed, you will find Napari Superres. And then we'll open this menu, and then you go and you find these acronyms that probably doesn't mean that much to you at the moment. So you will have found mastering here, SE, Sophie, Surfer, and Musical. These are the super resolution methods that are included into the plugin. Let's click, for instance, Measure, and Measure opens this this panel, which you can control it. But then I think it's complicated because then you start having here like amplification factor, order, PS, full with a whole maximum of watt. So probably it will be a black box and you might think that those are magic numbers and you have no idea what to do with that. So the goal or the main goal of the demo session of today is that you don't have that feeling. You know what is happening behind, what is the software doing, and what is the mathematical processes that is doing. So let's go back to that. Okay, what is a super resolution based on fluorescence fluctuation? Typically, microscopy is about to observe teeny tiny things, but there is a limit inherited from the nature of life. You can observe, on average, things smaller than 250 nanometers, and there are several ways to push that further. For instance, there are new techniques like step microscope, what is one of the microscopes that Tobias mentioned that are really fancy, and fancy unfortunately means expensive. So most of the labs around the world doesn't have access to that. So there are another approach to do that is processing the information statistically. But which kind of information? So let me show you here, we have some nucleus of BPI cells. And well, you can see there is some structure. There are like, I don't know, somehow bread somehow. But you cannot see so many structures in the nuclei. But what happens when you start a movie? When you start a movie, you start to do dynamically over there, and it starts to appear regions where are like, this region is darker, this region is brighter, and then you can start distinguishing structures within it. This is based on the fluorescence fluctuation. This blinking is that fluctuation in the fluorescence. So when you do fluorescence, you have the fluorophores and they're excited by light, and then they can go to excited state and they relax again and emit light. That it depends on the fluorophore that you're using, and it can go to another trap state that is called the state of phosphorescence. When you have this kind of statistically blinking, then, well, you can apply mathematics and statistics to overcome the limit of diffraction of light. there are several methods. The analysis of the image started with SOPHY in 2009, and then evolved. This is the very beginning. Then a lot of other methods start to appear in the field. And today we will cover, as I mentioned, SOPHY, which is the very start, Surfer, ESSI, which is before Surfer, sorry, Musical, and finally Messer. All of them has features in common, but also they have the peculiarities that I want to clarify today. I want to mention right now that please feel free to drop your questions in the chat. I will try to keep an eye on it, but if not, please, Tobias, let me know. Also, feel free to raise your hand and unmute yourself and ask the question directly. As a reminder, this is a Latin American workshop, so please feel free to do it in Spanish in case I can help with the translation of the question if you don't feel very comfortable speaking in English. Okay, so let me start with the first method. But before the first method, sorry, common features among all these methods. I think that is something important to say, that these methods has to work with movies. It has to work with temporal stacks. As I showed you before, we have this movie because the dynamics of the statistics and the blinking that will allow us to extract more information. So you have to have a temporal movie of your sample. I'm sorry for the noise. I hope that that bothering. In order to do so, you have to crop or reduce your image in regions of interest, and you keep the time price of this subregion, and then you analyze it. So most of the methods that I will mention right now, they do this, and they select a working region of interest. I will call you that. Most of the time is based on the point spread function of your optical system. But as we will see further on, that there are other ways to also determine this work ROI. They're also performed
Julián?
as, yeah.
So, should I interrupt you with questions?
Of course.
So, okay, so there's one question in the chat about the fluorophores that are used for super resolution microscopy. So the question is if any kind of fluorophore can be used based on their fluctuations, or if some fluorophores don't have fluctuation, if you could, for example, even use autofluorescence, for example.
Yeah, well, autofluorescence will be really not very good because regularly is regarded as noise. But in principle, any kind of fluorophore can be subject of this kind of techniques. The most basic approach will be confocal, wide field confocal, and then you can go for more elaborated techniques like area scan or a structure like microscopy or something like that, or scanning this confocal. But the basic, I would say, is confocal microscopy. The fluorophores that you can use with confocal microscopy, you can apply to this technique. But a little bit of spoil of the presentation, there are one technique that might be not need this requirement. So I will show this. Yeah, and autofluorescence has a fluctuation, but probably in your analysis will be regarded as noise. Okay. So thank you for the question, Tobias, and please keep going like this. When you see some questions that I cannot see, I will happy to answer that. So the methods also perform somehow signal to noise classification. Sometimes it's quite straightforward, as in the example of musical, and sometimes a little bit more high, as an example of SOPHY, but we will see this in detail later on. All of them, they do this temporal statistical integration of the analysis that they do over this movie, over this time stack. And finally, and I would like to stress this, all of them, they do interpolation. So you have your image with an X and Y number of pixels, and then you increase the number of those pixels. I have the figure that tried to figure that in here. Picture that this is your original image, and then you want to subdivide each of the pixels in more pixels. In order to do so, you divide a pixel, and then you have to interpolate. You have to guess mathematically which one is the value that corresponds to the created new pixels. There are different approaches to do so. Each of the methods that we will check today has a different approach, but the idea behind of all of them is that you create new pixels to have a new image, a bigger image, and that is a really important part of increasing the resolution. Okay, now I think we are ready to jump to SOPHY. As I mentioned before, this was the very first method. And SOPHY, what it does is a statistical analysis with higher statistical analysis with moments. Pretty much, it's hard to describe without the equations what are these moments or autocumulants, but you take the information in each frame and you gather together with the next frame and the next frame and the next frame with a little bit of weight. In this case, you use moments that are ponderated with a power. So that is the thing basically that you're doing here. There are different approaches and different mathematical ways to implement that. But the thing that I would like you to keep in mind is that they are gathering together the information along the time in each of the pixels and then integrate it. And of course, you do the interpolation to make an image bigger. Something that I would like to comment in here is that the team that developed SOPHY has developed PySOPHY. PySOPHY is a really powerful tool. It's not only for increasing or reaching super resolution, they are also really good by denoising, and they apply different kind of shrinking kernel deconvolution that are really useful for different approaches for denoising or for increasing contrast as well. So if you're curious about that, I will highly recommend you to try to check PySOPHY. Okay. I think that we don't have questions at the moment, so I will keep going. So as I mentioned before, the integration, the statistical integration with higher moments is done like this, and increase with time lapse. One thing that is relevant to comment right now is that images are quite big, especially if you have a stack with several images, you will take a lot of computational time. One of the main disadvantages of SOPHY, I would say, is that it requires a lot of frames. That is another feature that is important to keep in mind when we are comparing and we are exploring these super resolution methods. Some methods need less frames in the time, and other ones need more frames in the time. SOPHY is one of the needs the most to do this high order statistical analysis of the images. Moreover, it has really good results. You can see this is the original image. And then by applying the SOPHY analysis, you can increase the resolution and the contrast. You can go from here to here. You cannot even distinguish there are substructures in here while you can do it in here. This is the part of increasing the resolution that is really important to us. Okay, I think that this is the very basic comment about SOPHY. Let me jump now to ESI. ESI stands for Entropy-Based Super Resolution Imaging. Again, please keep in mind that we are working with movies or temporal stacks. So the thing of the base part that is ESI doing is using the information entropy, which is a really powerful tool because allows you to detect this blinking that I mentioned before. So you have the probability in here that in the next frame, you have the fluorophore in a state that is not the same as before. So if the sample that you have is not blinking that much, the probability that the state of the fluorophore remains in the same state is 1. So the logarithm 1 is 0, so the entropy will be 0. So you can see in the graphics in here. If it's blinking, you will have some entropy. If it's not blinking at all, you won't have entropy. So that is how you distinguish or how you gather and collect the information that you have over there. Of course, naturally, allows you to distinguish between kind of noise. You can distinguish with this approach, with its white noise and pink noise and so on. Also, another way, another really nice way that they use entropy is to compute the interpolation. Since the image that you're sitting here, they compute the cross entropy to set the value of the new created pixels. So that is what is doing entropy-based super resolution, is using entropy to detect the fluorescence or the change in the fluorescence, and is also using entropy to compute the interpolation parameters. In addition to that, also entropy is used to do the integration along the time. So you can see that is same equation, same concept applied for 3 different features to process the images, which I think is beautiful. Unfortunately, it doesn't provide really outstanding, or at least compared with other methods, results. But yes, you can have a really good improvement in the resolution. For instance, take this image, which is the ground truth image that they acquire, and they managed to feed this Gaussian to this Gaussian emission. After doing the ASC analysis, you can reduce the full width half maximum of this Gaussian significantly. I would say at least is 2 sigma the reduction, which is something really, really, really good. Also, pay attention to this part. Somehow the noise increase the contrast and allow you to observe clearly the substructures that are hiding in here. So this is the aim of this kind of approaches. Okay, again, this is the most basic thing that I need to mention about AC. No questions I can see. Okay. Let me jump now to Surfer. Surfer is a really powerful technique as well. And the concept, again, is cropping sub-images from the original images. And this is what I call it a working region of interest. So in that working region of interest, you will be looking for the radiality maps, which are not other thing than gradient fields. You compute the gradient fields, that means the first derivative of this subregion. Picture that you are selecting only 3 pixels on the original image, and then you apply this operator, which is the first derivative, to find the gradient fields or the radiality maps, which they are referred to that. When you do so, you manage to find the peaks, the local maxima in these regions, and then you assign with this criteria the new values that are created in the interpolation part. So that allows you 2 things: to select the local maxima, and since you have the local maxima and you have the radiality field, you can reduce again the full width half maximum of the Gaussian. In this part, it's important to mention or to be clear that we always approximate the punctual sources of light as Gaussian distributions in the intensity. So I hope that it was clear even before that I mentioned this. So you manage to reduce this Gaussian distribution of your punctual source of light, and then you have really, really nice results. So you have these sources that are together, but there are overlap and is already pixelized. You identify the reality stack, you do the analysis over time, and then you manage to distinguish these two punctual sources. Allows you to do something like this. You go for something that is quite blurry, not able to distinguish structures within it, and then you apply Surfer and you have this beautiful, beautiful increase in resolution. And also you are able, again, to observe structures that you weren't able to observe before. So as you see, is all the methods that I have mentioned and I will mention have this goal in mind to allow you to observe things that weren't clear before. There is information that is over there, but there is a way to extract more and to easily observe that. Okay, with that, I will jump now to musical. For the sake of the presentation and also for the sake of clarity, I won't saturate with examples of everything. I will cover in some extent the theory of the methods, but I will do the demonstration only for musical and measure. And this is the missing tools that we are about to explore, musical, and musical is one of the actually be presented today as a demonstration. So musical is also really beautiful, I would say, because it started based on theory that it was used in sonars, this kind of technology that used in submarines to detect objects and to process and analyze this kind of information. It was called music before, and now it's called musical for the image processing. So we have multiple signal classification algorithms for super resolution fluorescent microscopy. The main idea, the core idea of musical is to compute the eigenvalues of the images, of the regions of interest of the images. So remember that you have an original image, you select a working region, then you crop this region along the temporal stack, and then do the analysis of the eigenvalues of each of these frames. And then you keep the values, the eigenvalues that are not singular. That is really powerful because you are able to distinguish between noise and Poisson noise from these images. So this is a criteria to identify noise. And the criteria is established by the inflection point. This is the inflection point on the singular values of the eigenvalues. And when it starts to bend, that sets you a threshold for your imaging. As I said, part of these methods are based on signal to noise ratio classification, but it's not a thresholding arbitrary. It's well-defined and well-computed in this example. So it's quite powerful in that sense. Another thing that is interesting from this method is that the computation of the eigenvalues, the computation of the interpolation, and the denoising is all carried at once because it's linear algebra. So you have matrices over there that you multiply together. So the code is quite interesting. It was mathematically challenging. And then you have all this process that I just mentioned happening at once, just applying and multiplying vectors in the software, which I find it beautiful. After you have this process done, you will come out with one single result, which is your result working region. And then you stitch it together to reconstruct the final image. You have some examples in here. They create synthetic data to benchmark the results with another kind of results. For instance, you identify measure in here that I already mentioned, and you have something here that I already mentioned, and they benchmark it like this. You can see that, of course, with this display, musical is the one that is having the best results. But to make this interesting, I would like to draw your attention to the center. It's clear to us that you have 4 circles that are intersecting, but in the center, you cannot see a thing. You just see a bright spot, which I will say all of the other samples also fail to do that. Okay, so as I mentioned, I will do actually a demonstration of musical. So let me go to Napari. And since we already have the plugin installed, we are ready to use musical. Let me open my dataset. Okay, here is it. This example that I am about to provide is actually an example of the musical group that they are providing. So once you open your data set, you check that it is a movie. Remember that for most of the methods that we are checking today, we need movies. So this is what you can see from the movie. It's not as clear as in the previous video that I showed, that by observing the blinking, you can have more information about the structure. But let's see what musical can do. So let's go for the plugin. And then you go for musical. Okay. So then you open your image, then you open your panel to work with musical, and you have several factors of several parameters that you have to set. But what is that? The emission wavelength is the emission of the light that is coming from your sample. Remember that we are thinking basically on confocal microscopy or fluorescent microscopy, I would say, sorry. The numerical aperture is the numerical aperture of the objective that you use to collect your data. The magnification is as well the magnification of the microscope objective that you use. But for instance, picture that you are later on or tomorrow and you want to play around with it because you find that it's somehow interesting. And then you come in here, since it is not specified which is magnification, then you say magnification of what? Of my image, of this as the magnification that I want to set in this software. Then I would like to refer you again to our manual. So you go to the manual, you can surf in the manual, go to the musical part, and then you look for magnification. You go straight forward here, and you have a really short definition of what is going over there. And you see is the size of object image increased when observed through a microscope. That means it's the magnification of the objective that you are putting over there. So please, if you remain curious, is as much as you need the manual and the guide that we are providing you. As a reminder, you can find this manual directly in the web page of the workshop, and it's supposed to be here. And yeah, so the manual, I put it.
User guide, if I can suggest, you showed before.
Yeah, here.
Yeah, thanks.
I just mentioned it as the because it contains also the instructions to use it as a guide to do the graphical installation, but it contains everything. So please use it as much as you need. Okay, so going back to the analysis of the image, we have here the parameters that are already selected for this image, which I mentioned before is the sample that musical team provide. And the pixel size, in this case, the pixel size is the pixel size of the camera that you're using. There are some parameters that might be difficult to get. Yes, sorry, what? Okay, sorry, as I said, this is the pixel size of the camera. And this might be a parameter difficult to find or to get if you are not really into the lab or you don't have a really good communication with your technician in the lab. So, okay, that is something that can be improved with all kinds of methods, and I will comment on that later on. So the first thing that you have to do when you want to use musical is to set these parameters. And then when you are already set with this, you have to plot the singular values. When you press plot singular values, you will have this plotting here. And this plot might be set as float. And then you can drag it and make it bigger to observe it better. So remember, these are the singular values plots, and the inflection point of each of the sub-working regions is the important part to detect which is Poisson noise and what is the relevant information that you have. And that is defined by the threshold that you will find in here. This is a parameter that will change depending on your own images. But let's say that it starts something like -2 and goes up to -7, -8, something like that. I would say that the average of a safe parameter to use is -0.5. And that is the value that is set in here. This is really important to denoise the images and to correct processes the images. So if you are happy with it, you can put back the plot here. And just to don't lose it, you can come back to the plot if needed. And then alpha. Alpha is a parameter that is in somehow heuristically that it also provides help about how much to ponderate the noise. So once you have the threshold and you have this information, you want to also say to the software how much do you want to ponderate the noise that you have found over there. And it's information about the blinking of the fluorophores again. So unfortunately, this parameter is somehow heuristically, if you want to use it, you will be required to play with different parameters at the beginning. Once you develop a feeling of the ideal or more accurate parameters for your data set, it will be easier to find it. And then here is pixels per pixel, which I'm asking 20. Remember, this is the process of interpolation. So in this case, I'm asking to get 20 new pixels for each of the pixels. In the other sets, or the other parts of the plugin, you will find this interpolation parameter as the amplification factor. And this is not consistent itself with the other parts of the methods of the plugin, because it wants to be consistent with what authors already published. For instance, if you already used Musical before in any other platform as MATLAB or what is capable to provide. Okay, you have here your activity. Now it's done. And there it's it. Let me try to make clearer this image. Let me increase a little bit the contrast. Maybe even let's try to set a little bit of color of it. So this teeny tiny thing in here is the original data set. I can play it so you can see that is the original data set that we were providing to the software to process, and this is the result. As I showed you before, the image weren't clear and you couldn't observe any structure. But after processing with Musical and having the integration, of course, after processing the image, and you will have only one image. You won't have the whole stack again because the information was put together in the result image. And then you can observe structures and you can observe regions that are brighter than others, and you can go for something that is pretty much a lot of noise to something that is actually a really, really, really nice image, and probably is related with structures that is well known. In this case, there are mitochondria, and as my colleagues mentioned to me, there are actually structures that make sense to observe. So that is a really nice thing in here.
Julián,
do you have, yeah.
Why is this output still a video?
The output is not a video. No. The output is not a video. The video is just the original stack that we process. See, as you can see,
Okay.
I will play again the video. The video is just for the original stack. It is blinking, while the result is not blinking at all. Yeah. Thanks for the clarification. Yeah, I don't want the people to think that the result is a video. This is really important to stress. The result on all the processes, images that we are doing is never a video. It's one single image, because you are putting together, you are doing a statistical integration, and then you have a one single image as result with all the information put together in that image. Yeah. Thank you, Tobias.
Monara, you have a question as well.
Yes, about the video, I was waiting to ask that, because the video you create is based on the Z stack, or you do acquisition through time to make the video at the end for this analysis?
Yeah, no, the thing that you do is actually you go to the microscope with your sample, and you take images with the same sample at different times, and that is what we are providing. That is what we call the movie, or the C stack in time. Yeah.
So it's 2D images, it's not 3D.
It's 2D images, correct?
Okay.
It is not 3D.
Okay.
It is not 3D. That's correct. Yeah. Okay. Thank you very much. Any other questions?
There is a question in the chat by Luciana. She says, "Hi, how many images need to be taken, or how long is the video?"
Yeah. Okay. That depends on the technique a lot. For instance, regularly when you are doing this kind of fluorescence videos, you don't need that much. You can take, for instance, images separated by 1 second or so, because the fluctuation of the fluorophores happens in the region of nanometers. So in 1 second, you have, or even picoseconds, sorry, you have plenty of fluctuation. So you can have like these movies, really short movies. And in the case that I'm showing is just 100 frames. So there are a minimum of frames that you need. There are techniques that, for instance, are really okay with 10 frames, which are like, for instance, Messer. Or there are techniques, as I mentioned before, Sophie, that requires at least 100 frames to be providing good results. Yeah, no, it's not the raw result, it's the whole image reconstructed, sorry. Remember that you work in a ROI and then you stitch together the results of each of the ROIs, and then you reconstruct the full image of your data set. Yeah. Okay, my pleasure. Thanks for the questions. Please keep going like that. Don't be shy. Okay, so I think that
I have another question, and maybe we'll get to it anyways, but you mentioned this oversaturation earlier. So I guess that is an issue with any technique. If you oversaturate your signal, you don't see the fluctuations, or is there a way around this?
Yes, of course. You have to be able to observe as better as possible the fluctuation. Of course, if you saturate your image, or you have these so-called hot pixels, will be an issue. In principle, the methods can handle it, but of course, the better your data set, the better the results. But it's not ideal, of course, having this saturation. Yeah. Any other question? No? Okay. So I will go further with the presentation. So we already have covered musical. Let me jump to Messer. Messer, I must recognize that I'm quite biased because it's a technique that was developed at home, as I mentioned, by my current PI, Adán Guerrero, and he's at the moment a student, Slay. Slay is a really good mathematician, and Adán Guerrero is really good microscopist, but I think saying just microscopy is being a little bit short about that because he's good at another fields as well. Okay, what is Messer? And what does Messer? Messer stands for mean shift super resolution technique. The mean shift approach or mathematical computation of images has been often used to segment image. I think since 1980, the mean shift theory was used to segment image in the microscope field and other image processing field. But they take this theory and enhance it a lot and change some approaches to the theory to come with a technique that allows you to increase resolution, to reach super resolution. And that is one feature that is really interesting about Messer, which is it is able to improve the resolution in one single image, which is quite powerful. But let me start with the basics. So the thing what you do is, again, you have, for instance, a ground truth image, take it from some confocal, for instance, in here. You define, in this case, the working ROI by defining the full width and half maximum of the point spread function of your optical system. That defines the minimum structure that you can resolve in your image, and that is the region that you keep to work. And what work do you do in this region? Is two things. First one, you use a Gaussian mask to do a Gaussian weighted average of the information that you have in there in the spatial sense of the image. And then, remembering the intensity, here we are depicting the intensity as a Gaussian distribution. You apply something that is so-called kernels, or the shadow kernels, that at the end of the story, just to simplify, maybe some mathematicians will kill me if I say this like lightly, but I think it's a good way to transmit the idea. You are doing weighted average on the space and in the intensity, and then you put this together to increase the resolution. This is analogous to a second order operator. So you are looking for the second derivatives. So if you remember your calculus courses, when you take the second derivatives, you find inflection points, which clearly are those for a Gaussian distribution. So that is something that I like to highlight. So once you apply a measure theory to an image, you will find this. And the measure has to be inverted. You remove the negative part, and then you have something that has the same properties, the same ubication, and if you multiply for the original image the same intensity, but with the reduced full width half maxima of the point spread function of your image over there. That is the power of measure. That is the essence of what is doing measure. You apply measure to a Gaussian distribution, and it narrows it down to a factor that could be up to 2 sigma. That is another important part of it is that it can be iterative. So you can do iterations over it. You can apply again measure to these measure results. We call the first step measure 0, but then you can go for measure 1 and you apply it again, measure 3, measure 4, and so on until you remain with nothing. So be careful with getting too excited with measure higher orders. Okay, so as mentioned, all these methods works with a statistical integration of the stacks of the movies. So you apply this, which is called single frame measure, to each of the frames of your stack. And afterwards, you integrate that information in different statistical approaches. So let me show you that. And let me give you some feeling about the parameters and the features of measure. So we are already done with musical. We erase this. We go to plugins and we look for measure. Let me open. I will use this synthetic data set because it's really, really small and is easier to show features with this one. Otherwise, the demo session will be way too long. Okay, so as you can see, this is a simulated data set, which mimics the blinking that will be occurring in a real sample in your confocal microscope or your fluorescence microscope. So this is the data that we will want to analyze. So I will set the parameters while I will be commenting on it. The amplification factor is how many times we want this image to be bigger. So in this case, I will apply 2. So with this, I will obtain an image that is twice bigger than the original one. Order is the order of measure, is what I was just commenting right now. How many times do you want to apply the theory and the processing image of measure? I will recommend always starting with 0, because as I mentioned, if you exaggerate with the iterations, the times that you apply measure, you will lose information. In general, I will discussing this with the team, and we agree that it's not recommended to go higher than 3. There are some times that it's good to increase the order. There are some times that it's not good to increase the order, but you won't find never a case in which you need to go for an order higher than 3. Okay, the PSF full width half maximum. Remember that this is a parameter that is inherited from your optical system, and you have to establish this value, which will be the working ROI of the measure process. In order to do so, you have this button in here and appears this calculator. In this, it will be asking for the optical parameters of your system, which will be the refractive index of the medium. If you are coupling your objective with some oil, you will have to provide this parameter as well. If you are not coupling or you are not using immersion objectives, then you just set 1, because then you are working in air. The numerical aperture of your microscope objective, the emission wavelength of your sample, and the pixel size of your camera. Remember, these parameters also were required by musical. But we tried to do a clever approach in here, and we use something that is called the correlation. So you can use these parameters if you have it at hand, or you can go straight forward for the correlation. The correlation, what it does is go It analyzes the images in the Fourier space, then it masks the images until it finds the maximum frequency that is observable in your image. And then you can correlate this with the neighborhood in pixels. This is way better because picture that you have your latest iPhone over there, it has an amazing camera. But if you try to run with it or the illumination is not really good, the quality of images will vary to image. And then there is a property of the circumstances, not the optical system per se. And the correlation takes that in account. And also, I would like to say that it's way easier because you forget about these parameters. And then you just click the correlation because it does an analysis over the image. And I don't know if you noticed, but the number over here already changed automatically. I will repeat this just to be more clear. So you press the correlation, the window will be closed, and the number will change. That will be the working region that is set by the correlation of the system. Then I think I will stop here just to don't make this confuses. So we can apply measure now with these parameters. Minimizing messing is just a denoising feature because when the interpolation type is set as bicubic, the bicubic interpolation is prone to do some pixel or meshing artifacts. So then when you compensate this, you normalize the intensity of your image, and that's it. We are ready to compute measure for the stack that we have in here. So if I press run right now, it will start computing the results. And please notice, let me increase a little bit the contrast so it's easy to observe. So this is the result. Let me put together. This is our original data set. This is the result. As you can see, it's twice as bigger as the original because it's what we asked. But it is still a movie, right? This is the single frame analysis of measure of each of the frames that has been provided in the original stack. But what happened, I was just mentioning that you had to have a result of one single image to gather together of this information of the blinkings of the fluorophores. That leads me to talk about temporal analysis. Did you click temporal analysis? This menu will be displayed and will ask you that which kind of temporal analysis do you want to perform. So you have temporal product mean, the variance, the mean. You have SOFIs. Remember that SOFI are higher order statistical analysis of the integration of the temporal dimension, and covariance and sigma times coefficient variance factor. Then you can select one of those. For instance, let me start with, I don't know, mean, which is quite straightforward. Something that you have to keep in mind is once measure compute the single frame measures of each of the stacks, you have to select it and you don't have to redo all the calculation of the time, so it will be really fast. So you have here, this is the result that you obtain with the mean of your single frame measure. Here you can see that it's no longer a movie. Is just one frame as we were expecting before. Remember that I mentioned when I said, I was talking about SE, that you won't be able to distinguish the center of the intersection of the circles, where with this integration, you cannot see it neither. But let's see what happens if we change to another kind of statistical integration. Let's do something like this. No, this is not the one that I want. You have to select the original stack. And then you go to the statistical selection that you select, and then you press run. That is the one that I wanted. In order to avoid confusions, I don't know if you noticed in here, but the images we're adding with the name that they belong to. So first we have measure, then we have the temporal measure and the type of statistical integration that we perform. So we can compare the mean with the coefficient times sigma. And that is something really, really nice. Maybe I increased way too much the contrast. Here, I think you can see it better. With measure and this type of statistical integration, you actually can to distinguish the intersections that weren't observable before. Here is not providing that many details, but in here you have way more details. Actually, that is the thing that we were looking. And if you want to compare with the original, you can see that it's amazing how you go from this, because you identify each of the circles and then you reconstruct the image. But even in the original video, you cannot see the intersection of the circles. But if you apply measure, then you have information about the structures below this. Okay, something.
Julián,
this is about, yeah.
That's really impressive. Thanks for demonstrating this. And there's a question in the chat. Navanita is asking, in musical and measure, how do we distinguish artifacts from real signal in the final reconstructed image?
That is a quite huge deal that you were, oh, but I just saw your comment about measure. It sounds like knife in German. And yes, that is, thanks for the spoil, because it's the next generation of measure. We are doing some changes and we will bring the knife soon. Yeah, there are different ways to address these questions. There are different ways to benchmark the information that you do. For instance, I think the best one at the moment is called a Squirrel. A Squirrel is coming from the surfer group. And this is the aim. How do you know that you are actually getting more information and not artifacts? That is a quite big and difficult question, because, for instance, in artificial intelligence, you have your ground truth data, and then you just can benchmark with it. But in principle, you have to do super resolution, because there is no other way to attain these kind of structures. The most basic approach that I'm commenting here is that approach to your expert. As I comment, for instance, in the mitochondria, you show this image to the mitochondria expert and says, these structures make sense to you or not. It's like in the sense that I mentioned here with the 4 circles intersecting each other. Like, of course, we were expecting to observe these intersections, but in the other approaches we couldn't see. So you have to have really clear what you expect, even though that you haven't seen it before. And eventually we will include a Squirrel or another kind of approaches to try to benchmark automatically the denoising or the biasing that you might induce with these methods. Yes, thanks for the question. Yes, of course. Actually, the question is, have you ever compared these super resolution plugins with Eriscan processing? Yes, I think that I'm ready to spoil this, Rocco. I think that you don't want to disclose this too soon, but I think we are in confidence. Recently, like 1 month ago, I had the opportunity to visit Rocco at the Francis Crick Institute, and we did this. Actually, we did it with Eriscan. And we obtained really good results. But one of the things that we did, and I was really impressed, especially because we did it for measure, was using multi-photon microscopy. We use a really low intensity of the laser. So the signal to noise ratio, it was really, really, really big. It was pretty much just noise. And then we acquire image with the proper illumination of the laser. One of the problems when you go for a high power in the laser, when you're doing multi-photon, is that you might damage your sample because it's a lot of energy. You can create little bubbles. And we were really impressed because with measure, we were able to retrieve the same structure in the multi-photon with the proper illumination. So yes, we have done this kind of benchmark. Not extensively, but we are preparing this publication, yes. There are no more questions. No, I think we are covered.
Yes, thank you,
Okay.
Julián. We still have time for one more question if someone wants to unmute themselves.
Okay,
I think it was already very interesting and clear.
perfect. So if there are no more questions, I think I will quickly wrap up the presentation. I think we are approaching to the hour. So
Yes.
the last thing that I want to comment and to mention it is like, what happened if you say, okay, for instance, the amplification factor is a factor that allowed me to increase resolution. Then instead of putting 2, let's go crazy and let's put 5. But that is not very crazy, but there are people that put more. But let's put 5. Let's see what happens. You have the activity over here. And you can see that it's significantly taking more time, right? In the previous example, it was almost immediately, and now it's taking way too long. And let's see, of course, if your image is actually way better now than before, it's worth to wait, but sometimes not. This is one kind of the feeling that I want to provide you. Like the parameters that are preset in the plugin are really close to the ideal parameters, at least of the samples that we managed to find. So feel free, please be curious, please explore it. But I wouldn't advise to go that further away or change it that much, at least at the beginning. While you are using the plugin, you will develop this feeling of what is better or what is not. You can see this is a 5 times amplification factor. That means that we have a figure that is 5 times bigger than the original. But I would say that we didn't earn that much. We already retrieved this with the 2 times amplification factor and the BSF that we originally set. So to wrap up this presentation, I would like to comment that all the methods are different, and then they perform different with different data sets. So be curious, explore all of them, and try to see which one is the best for you. And also, once you reach the parameter part, be curious and also play with it. But I hope that after this presentation, you have some criteria and what means explore these parameters. Just to finish this, I want to mention that Messer is indeed capable of working with one single frame. I think that this might be the most interesting part of most of you, because then you don't need to have these fancy images. Let me open just this sample that is preloaded in Napari. I will use cell, and I will apply Messer to cell, and just see what happens. Okay, and we are ready to run. If I put 5 in here, it will be taking ages, so I will just put 1. Let's compute it Messer in here, and this is the result. Notice that I didn't use a stack, it's one single image. And also please notice that I'm cheating a little bit in here because this is bright field. In principle, of these methods are only for fluorescence fluctuation. That means dark field background. But check this out. You manage to retrieve really nice structures. This is amazing to me because when you see the Messer result, you see, oh, okay, you have this point in here, you have this section that is darker. For instance, this really dark section now becomes really clear in the original image. These bright points surrounded by these dark areas now are really clear. You can match the structure that you couldn't see before. So with this, I want to comment and to say that Messer is one of these providing more interesting results because apparently is quite powerful even with one single frame, and also seems susceptible to be suitable for bright field. So please be curious. Please try to play around if it's in some interest for you. I have some examples in here, but they are a little bit redundant at the moment. And thank you for attention. If you have any question or you would like to get help to analyze your images, I will be more than happy to support you. Thank you very much.
Thank you very, very much, Julián, for a really great presentation and demonstration.